So I have given you some background to the non-linearity. That means non-linear behavior of beams. And there are two kinds of non-linearity. One is called geometrical non-linearity, other one is called material non-linearity. One occurs because of change in geometry, other occurs because of material goes into plastic or inelastic. It is called also inelastic. Elastic and inelastic. Inelastic is that zone when you remove the load, then it will not come back to its original position. See, after that, you know that. So it is called inelastic or plastic. Plastic is so now this non-linear analysis is very complex because it has to be done step by step. So maybe you will have to do 1000 steps in order to plot the P delta curve. Complete P delta curve one has to do 1000 because you have to take very small steps. It is a non-linear, no? So we will assume that, okay, let us assume linear behavior in that small delta P. Linear behavior in that small delta P, and then we will find out the slope. So like this we can go and find out the total load deflection. So that is a very So we will take a simple example. There is a beam having some depth, and it is, you may wonder why we take always simply supported. Why not cantilever? Yes, we can take cantilever also. Simply supported, and then it is subjected to load P here. We would like to find out what is the maximum load that we can apply to this load, this beam. Maximum. That means when it fails. Now so this beam, the line diagram for this beam is like this. This is the ideal line diagram you have drawn through centroid. And then the bending moment diagram for this beam is like this. Now please, I do not want any talk in the class. If you have to talk, my dear friend, yes, if you have to talk, you better go out. Both of you go out and then talk. One thing I am finding that this beam has got maximum bending moment in the center. The maximum, if I plot maximum bending moment in the center, so what will happen? Here if you see the depth, because of this will be under tension bottom and this will be under compression at the top. Because this is how it will deflect. It will deflect like this. This is the deflection diagram. So tension, compression. So sigma x, we can find out sigma x. Sigma x will be m into z by I. Later on you ask me how come I have drawn a x-axis and the support is here. So you should ask such things. So mz by I. So mz by I, the stress diagram at the cross section where the maximum bending moment is there, it is something like this. This is the stress diagram. This is sigma x, this is sigma x variation, and the fibers are stressed. So this is tension, this is compression, and how do you get moment? See, this will, you can take the centroid, you can integrate from this, and that will be acting from the centroid. So this will give you a compression C, and this will give you centroid. If you integrate this diagram, that will be acting through center. So that will be a tension T. And this will form a lever arm LA. This is lever arm. This is centroid. Centroid of a triangle will be at what depth? 1/3 of h by 2, h by 6 from here. This will be h by 6. This also will be h by 6. What is this distance then? From here to here. 2 by 3 h. नहीं 2 by 3 h, sure. Four, 6. So lever arm is 2h by 3, lever arm. And this lever arm is the one which produces the moment acting on the cross section. I mean, this equal and opposite forces, one is compressive force, one is tensile force, and they will give you a moment, and which is acting at that section. So you must realize, after all, moment comes from where? Moment comes from the stress distribution. Stress distribution, again, because of stress distribution you have forces, and that must form a couple. So this is a couple which is formed. So what I am trying to say, that yes, a time will come when this extreme fiber will reach, because you have this simple diagram. A time will come when this sigma x at h by 2 will reach sigma y, will approach sigma y. Is it okay? Plus minus h by 2. Okay. Sigma x, because if it is symmetric, it is plus minus h by 2. It will approach sigma y. So what happens then? So then that fiber, extreme fiber of this here, will become plastic. So I will show the plastic zone like this. It will become plastic. It will become fluid. Plastic means it becomes fluid. From solid it changes into fluid with viscosity, viscous fluid. So it becomes, so it can just now elongate, just like your what you eat, chewing gum. Yes, something like that. And they sell for small children, so it will just, it will elongate. So then what happens? Then you load it further, and your load diagram also is there. I think somewhere I should draw also P load and load. Load is increasing. I'm increasing the load. So there is a load diagram also. P delta. So we are here somewhere, not that we are here. Sorry, we have now, once this is plastic means, yes, somewhere we are here. It is just beginning. So it is just beginning. Afterwards, what will happen? After this load cannot be, there will be a jerk. load will not follow a linear path. Once plasticity starts here, there will be a jerk. Slope will change, so this will change its slope and it will become something like this here. Load displacement. Okay. And then you load it, again it will go, it will take load, but then it will be changing the slope. It will become flatter. See, here it will be, slope will be more, but as you go more and more, because more material now, as load increase, silence, as more load is applied, so this area, that means bigger depth, this one is now becoming plastic. This much has become plastic now in the center. So plasticity is flowing through the depth. Plasticity, this section, because this is the section where maximum stress is occurring. There is only one section in this beam. This is hinge. It will rotate. This is also roller. This will also rotate. Okay, so maximum bending moment is only one point. So this is the maximum stresses are going to occur here, not anywhere else. So this plasticity will go on increasing, and at times, so this process will go on increasing, till this top and bottom meet. And the middle fiber, that means neutral axis, also becomes sigma y. Neutral axis, the stress level at neutral axis is also equal to sigma y. So that means this entire thing has become plastic section. So what will happen? Yes? Why? Because loading is increasing. P is increasing. Load is being increased. Load is a monotonically, it is going from 0 onwards further. Where is sigma y, my dear friend? So we are saying only bending stress. We are not talking about shear stress, first of all. We are taking only one stress component, bending stress. And we have drawn all these for bending stress only. So we are saying as load increases from 0 onwards, then this is the status. This section at the section at the, now I can draw the line diagram. Now the entire section, entire depth of the beam has become plastic. So in the center there will be entire depth has become plastic. So this is physical hinge. Hinge means what? You drill a hole in the plate, put a nut and bolt. It can rotate like this, free, no movement. No movement, only x displacement is 0, z displacement is 0. Hinge means at this point the displacements are, it cannot move in x direction, cannot move in z direction. It can rotate, it has a freedom to rotate about y axis. And similarly this one only z is 0, it can move in x direction. Roller means it can move in x direction. So this is the difference between a hinge and a roller. It can move in x direction, but it can also rotate about, this end can rotate about y axis. Rotate. Okay. So then, how is the stress diagram? What is happening to the stress diagram? Stress में क्या हो रहा है? What is happening to the stress through this depth of the beam? This has reached sigma y. First, extreme fibers reach sigma y. Then the plasticity started flowing into the depth. So that means next also it will become a rectangle. And then, of course, then this. Then this will be there. This is like this. At that stage, some value of P, there is a P here. Okay. Okay, so this, then again, as P increasing, this is becoming like this, and then this line is becoming like this, because this is elastic, this depth inside is elastic, but then this has become plastic. This stress cannot go beyond sigma y. So sigma y. So like this it is going on as load increases, and finally a point will come when the entire section becomes plastic, means this entire depth, half of the depth here is subjected to a stress level of sigma y compression, one side tension, one side compression. So this is tension, I think, bottom tension and top compression. So it will become a rectangular diagram, not a triangular diagram. Two rectangles, sigma y. Is it okay? Has everybody, because this is very simple. In fact, this is the simplest thing that we can think of. So then so where is the center of gravity? This is compression, this is tension. It's very difficult to draw what is compression. Okay, so this will have a center of gravity in the center, and this will be the total C force. This will have again a center of gravity in the center of, that means h by 4, and this will be having T. C equal to T, tension must be equal to compression. Okay, so what is the value of C and T? Can you tell me? What is this distance? H by 2. What is C equal to? C equal to T is equal to how much? Area B into sigma y multiplied by H by 2 by depth कितना है बीम का? Half the depth multiplied by B. Cross section is, I am taking a rectangular cross section, B and H. So area B into H by 2 multiplied by sigma y. This is equal to C and T. BH by 2 sigma y. Then what is this? Lever arm, C into multiplied by H by 2. So BH by 2 into sigma y into H by 2. So what is BH square by 4? What is this value, by the way? What is this value? M. What M? When the entire cross section has become plastic. When the entire section has become plastic. So we call this plastic moment, MP. Value of MP equal to BH square by 4 into sigma y. So there is MP acting there. So this is called, first of all, this becomes, the beam breaks over here. See, when this becomes plastic fully, originally this was straight. I mean, understand this. Originally this was straight, and then now I think, let me put it on this. You can see it on the, yes. Now when it becomes plastic, then from here, because in between of course there will be some curve here, some curve will be there, but suddenly when the entire section becomes plastic, this will simply be a rigid rod, this will be a simply rigid, because there is no question of any bending here. This will be rigid rod. This will be straight, and it will form like this. Because in the same, it has become a mechanism. It is a mechanism. 3 point, one hinge. One hinge means roller also is a hinge, and then in center also there is a hinge. But it is a special hinge. This is called plastic hinge. This is a hinge, not like the one you have put a, you have nailed this and then put a nut and bolt. But yes, this is a hinge, and there is a plastic moment acting there. Because here there is no moment acting. Here it is free. So this point you have, when it becomes like this, so we say that the beam has failed, and this is the ultimate load capacity of the beam, and you have here MP acting, and this MP is acting on this hinge. Okay, so this is the condition when it becomes failed. So we will say that at this, when it becomes MP, this is the ultimate load PU. So ultimate load PU. So at this stage, this P will change to PU. So how to relate this? Because now you have got MP also, you have got, so how to relate? So this is, so you have now a situation so this is the free body diagram of the entire, it is not free body diagram, but it is the entire structure at the time of failure will look like this. Two straight lines, it is called mechanism. It forms a mechanism. It can be taken up and down like this with hand. But then this is what? So can we now find out the value of PU? See, PU, yes, this angle is what? Let us say theta. Of course, everything is small, so don't think that this theta is a real theta. It is a delta theta. This is displacement, which is, so delta theta. So I will say the work done by PU is L by 2 into delta theta. PU, from here to here it has come down. This displacement is how much? L by 2 into delta theta. Is it okay? Small displacement. This vertical displacement will be L by 2. Approximate. It is the arc of a circle. We are taking a small displacement still. We are not considering large displacement. This is based upon a small displacement theory. We are saying that this length, inclined length and horizontal length both are same, and then this distance is, so this is the work done, and that must be equal to what? This MP, internal moment that has created here, that is existing. So on this side as well as on this side, so 2 MP, both sides MP is there, and this has also done work, na? So how much? Moments do work on rotation. So that multiplied by rotation. Rotation is how much? This is also delta theta, I believe. Yes. This is also delta theta. The MP will do work over delta theta. So MP into delta theta plus MP into delta theta. So 2 MP delta theta. So this is the equilibrium condition. That means external work done. This is external work done. External work done is equal to internal work done. This is the basic principle. Work done externally, internally must be same. Otherwise, how did you find out MP? Because of internal stress distribution, MP has come. That is become equal to external load applied, external moment acting on the cross section. So external, internal must always be equal. So they have to be equated, and therefore PU, ultimate load that the beam can, is how much equal to? Please tell me. Delta theta 4 MP by L. And MP is equal to, in terms of, just now we found out, BH square by 4 into sigma y MP 1 by L. So कितना हो गया ये? You please write it. This 4 goes. BH square by 4 sigma y MP by L, 4 MP, 4 MP. So you get here BH square by L into sigma y. You can find out what is the ultimate load capacity of the beam. This is the maximum load which can be put on this beam, and it is in terms of B, cross-sectional dimension, H, length of the beam, and the yield stress. So everything is known. This can be found out in advance. There is no problem. You can find out all these things in advance. Have you understood the concept behind finding out ultimate load? So this is a very simple analysis, ultimate load analysis, based upon that cross sections are subjected to bending moment, and there is no effect of shear force on the bending moment. See, actually shear force also will do some effect. We are neglecting that, because any cross section will be subjected to shear and bending moment. But in this case, it so happens that shear force is 0 in the center. Maximum bending moment will occur when the shear is 0. dm V equal to dm by dx, rate of change of moment. So this is okay. So you have got a simple formula. So this is, we are covering now in this course. Earlier we were covering this portion in structural analysis. Now we have decided to cover this in solid mechanics, this concept of, now supposing you have, I will just take one simple example. Now extend this. Yes, time is. Sir is waiting. Okay. You do it for this problem. Now, this is there and P is there here. Please find out the ultimate load capacity of this. Then you please find out the ultimate load capacity of this. I will give you some simple, these are all simple problems. And one is P, yes, it is okay. Yes, these two examples you please do. Please find out what is PU. So this you do. Okay, thank you.